So one of the last topics that we're going to be talking about is going to deal with slope. So this is going to feel like a bit of review from chapter 3 when we started talking about linear regression and all of that. But this specific section will be on inference methods that we can use for slope. So basically what we're going to be asking ourselves is, again, is the slope 0, which means there's no correlation between the two variables, the response variable and the explanatory variable, or is the slope not equal to 0? Is it greater than 0? Is it less than 0? Meaning that there is some type of a correlation between the two. Okay, so here are some things that we've talked about so far this year. So we've got our predicted y. So we've seen this as predicted y is equal to your starting value, which is also your intercept, plus beta is going to be your slope, and then that's times x. And then some things to point out, just make sure, I don't know why I wrote a p there, that should be a y. Just make sure that you label what your y is and what your x is, because you always need to label those things. The mean of the sampling distribution, so that's going to be beta, that's going to be your slope. So slope is represented by beta, so just keep that in mind. The standard deviation is going to be this formula right here. You've still got your 10% condition, so that's your 10 times your sample has to be less than or equal to the population. We've already been doing that. And then approximately normal, we're going to be looking at a normal probability plot for this, and I'm going to explain that because we haven't looked at a ton of those this year, and you're never asked to construct them, you just need to know what to look for. The worst part about this, because everything else is going to seem very familiar, one, as I said, it's a review from chapter 3, so it's going to have predicted y is equal to your starting value plus your slope times your explanatory variable. Everything's going to be labeled. A lot of your conditions stay the same. It's going to be a mix of chapter 3 and then your inference stuff. So you still have conditions. But the worst part is going to be that there are 5 of them. 1, 2, 3, 4, 5. All 5 of them. You don't necessarily have to have them memorized because we can put them on your reference paper. But if you did, I do have an acronym for you to remember. Liner, sort of. So if you ever need to have it memorized for some reason, use that acronym. L stands for linear, so you just want to see, is it linear? Does it increase by a fixed amount every time? Right, so if it increases by a constant amount every time. Independent, that's your 10% condition, so that's your 10 times your sample has to be less than or equal to your population. Normal, for this one right here, we want to look at a normal probability plot and see that that is linear. Equal standard deviation, this comes from your residuals. When you look at your residual plot, you want to have 0 right in the center, and then you want to have dots that are kind of equally distributed. Like you don't want to have them all on the top half of the graph or the bottom half of the graph. And then obviously there's random, and we know why that's important. Or if we don't, remember random sampling means you can apply your results to the population. Random assignment means you can establish cause and effect. So let's look at this example really quick. So we have an experiment. They're dropping helicopters from different heights, and then they are collecting data to see how much time it took for the little helicopter to fall to the ground. In this first one right here, this is just your normal scatter plot. This is going to be your residual plot. This is just a histogram of the residuals. Now, you can also look at this one to establish normality. So you see that nice normal shape right there. So that's one way to establish it. This last one right here is a normal probability plot. And what you're looking for is to see if that's linear. So as long as it looks somewhat linear, you're good to go forward. So it says check whether the conditions are met. So is it linear? Does it seem like it goes up by a constant amount every time? I think that if we were to kind of guess and look at that, you can see that it increases by a constant amount every time. Independent, we've got 70 right here. So each one, I mean, I don't even know if we really need to check the independence piece because each helicopter is different, is independent of the previous one. Like there's nothing that means if one falls at a certain amount of time that the next one's guaranteed to fall that far. N is your normal, so you can see here either by looking at the histogram that it looks normal, or the normal probability plot is linear. E is equal standard deviation, so in your residuals, so if you look right here, that's your 0, and you can see the residuals on either side are pretty well balanced. And then lastly, we have R, which is random, and they were randomly assigned, so they were in random order. Okay, to construct your confidence interval, here's how you would go through that. So good news is they usually give you the standard error of the slope that's in the computer outputs that we've seen before, so you don't need to come up with those. I'm going to show you that in just a moment. So all you pretty much have to do is the slope plus or minus your t, which is slightly different, but not a lot different, and then times the standard error of the slope. So this right here and this right here is going to come from the computer output. So we've seen this many times. This right here is your slope, because the one this is constant is your y-intercept. So right here is your slope. So that's that little b. Little b means slope. Big B is your population slope. Little b is going to be your sample slope. Then if you look right next to that, standard error. So that's the part right there that goes in the second part of the formula for your confidence interval. So you really just need those two things right there. Now, to figure out your t, it's the same as before. So to figure out your t, you go over to table B, and then you still look at the bottom of table B. So you look down here at your confidence level. And then up at the top, you have your degrees of freedom. And this is the only thing that's different, is that your degrees of freedom is at now n minus 2. So you have the same amount, you just do n minus 2 instead of n minus 1. So what I mean by the same amount is you have the same amount of explanatory and response variables, so you just figure out what they are and then subtract 2. It's the only one that is different, is just when you're finding the t value for the slope. Oh, and by the way, why t? Because when you're constructing slope, it's an average. So it's an average between all of the points that are there. So that's why we always go with t, because it's, again, goes back to kind of your means thing. Okay, so the standard error of the slope, again, that would be that answer right there. So 0.002018. When you are interpreting, we need to get in this many. So if we repeated the random assignment many times, we would expect the slope of the linear regression line to vary by 0.002018 from the population slope, which to save room I'm just going to call B, which again you should get into context. And again, just to save room, I'm not going to put that there, but that's predicting the flight time from the drop height. Your critical value, again, you're going to look over at table B, which I think I did pull up this is the one that you get on the reference paper. It's slightly different, but you can see it's also very similar. So we're going to go down to table B, which should be right here. And then look down to here. So we are constructing a 95%. In that question there, we had, was it 70? So we would use 70 minus 2, which would be 68. So we need to go to 95. And then I would probably just use the 60, which is 2.000. That's going to get us close enough. Okay, so you can use your chart, but it should look very, very similar. So we would have to show your, I don't even know how you show your work, I guess degrees of freedom equals 70 minus 2. And then that would give me, I think we said t was equal to 2.000, if I remember correctly. Interpret the interval from part B in context. Oh, we had to find the interval. Oh, that's why we were showing work. Got it. Okay, so take your slope, 0.0057244, plus or minus your t value, which is 2.000, times your standard error, 0.002018, and then that will give us 0.0053 to 0.00613. And then we would say, we are 95% confident that the interval from 0.0053 to 0.00613 contains the true slope that predicts flight time from distance dropped. Explain the meaning of 95% confidence. This is that thing, you can use words, but just to save some time, remember if we took many, many samples and constructed these intervals, 95% would contain the true population slope that predicts the two. Okay? So this one right here, I'm not going to bring you all the way through it because I think we're doing okay. This would still have a state, a plan, a do, and a conclude. In your state, we're wishing to estimate beta, which is the true slope of the regression line that predicts what are we predicting? Predicts amount expelled from number of Mentos. And then we would also need to say at 99%. In your plan, you name the procedure. So this, for this name, this is a two-sample, I'm going to have to look up the name, but it's on your reference paper. Then you've got your LINER. So talk about all of those things. For the do portion, you go up there, they gave you the slope, it's right there. So 0.07083 plus or minus your degrees of freedom here. We have how many Mentos were there? 24, maybe. So 22, so you would go to 22 on here, which they do have listed. Okay, so 22, and then we would scroll up. We want 95% in 22, so 2.074. And then we have times your standard error of the slope, which is 0.01228. Type that in there, and then you get your interval, and then you conclude by saying before it's the same words as we used on the previous one. Just really, really quick, because I know I'm running out of time here. Nothing is different as far as your formula. So this is the same as before, sample minus hypothesize, which by the way, your hypothesize will always be 0. And then we are going to have either a one sample test, a two sample test, or a two-tailed test. So that's all, I'm sorry, a one-tailed test, a two-tailed test, or a one-tailed test, a right-tailed test, a left-tailed test, or a two-tailed test. And then we still have our n minus 2 as our degrees of freedom. Okay, so what is the equation of the least squares regression line? I'm going to let you guys do that. So remember that, just make sure you get the predicted. So we're predicting tip, I guess I am going to do it for you, is equal to, again, that's going to be your constant, which is 4.535, plus 0.03013 times the time that someone spent there, and then interpret the slope of the least squares regression line, 0.03013. I put that over 1, and then it's for every additional, I believe this is minute, the predicted slope increases, predicted tip increases by 0.03 of $1. R squared is your percent of variation. So you take that and you say 13.2% of the variation in the tip amount is accounted for by the least squares regression line. Please know how to interpret that. And then we have the do these data. So you still have your state, your plan, your do, and your conclude. In your state, you have your hypothesis, so you have your null and you have your alternative. In the null, we have that b sub 0 equals 0, so there's no slope. In this case, we want to see the amount of time that there's a positive linear relationship, so that will be greater than 0, where beta equals, put that in context, plan, name, and conditions. So LINER, make sure you check all those. For the do portion, you're going to find your t, which will be equal to the sample slope, 0.03013 minus 0. Again, that's always 0 over the standard error of the slope, which was 0.02448. That should give you 1.23. We're going to go do a TCDF on the calculator. If you look here, we're shading greater. So 1.23, shade greater. 1.23 is the lower bound. 10,000 is the upper bound. Your degrees of freedom, we had 12 tip times, so that would mean that that would be 2. And when you conclude, you're going to get a p-value of 0.123. So since p is greater than alpha, we fail to reject the null, which means we do not have convincing evidence that there is a positive linear relationship between the amount of time and the tip money that was left. Okay? Okay, so hypothesis test for slope. Lots of things that are similar, things that are different. I'm going to ask you to figure out what some of those are.